Number 5. This is a problem that's quite a bit different than the previous 4 problems that I've done, but this is not a very hard problem once you just kind of organize your thoughts here. So number 5 says, when you use a slingshot to fire a rock, the mass is given as 705 grams. So I'm going to straight away convert that into the SI kilogram, 0.705 kilograms. You stretch the rubber band, storing potential energy. Okay, so this is true. We haven't officially studied it yet, but we don't really need any special knowledge for this question. So I think it's a fair question to have here, but it's true. Things that are stretchy, like springs or rubber bands, or even in archery, a bow, they store a form of energy that we can call elastic potential energy. So it is a form of potential energy. It is not gravitational potential energy, but that's fine. We're going to treat this as just another form of potential energy for the sake of this question. I'll designate it as US for what we'll more typically see as a spring potential energy, even though I know it's a rubber band in this case. But I'll call it US just kind of as a standard symbol for what I'll be introducing later on. Okay, so it says if you stretch the rubber band so that it has 100 joules of potential energy, so I'm going to say US, think of that spring or rubber band in this case, is 100 joules. Okay, so part A says, how much kinetic energy will the rock have when it leaves the slingshot? Okay, now, to be clear, we're not looking at the projectile motion of this rock as it goes flying eventually to hit the ground or somewhere else. We're only looking at the actual launch of this rock. So initially, I'm imagining that it's held back in the slingshot with the rubber band stretched out. When you release, the rock moves a very small distance and it actually picks up speed thanks to that energy conversion of the spring potential energy into kinetic energy. So I don't really know what the height of this is, but I'm just going to say that the height that it ends up with is equal to the height that it started with, which I'm just going to think of as the zero height for convenience. I don't need to know how high it is. The point is that there's no vertical motion occurring in this question, considering only the launching of that rock. So I can just kind of conveniently set a height of 0 wherever I want, and that way I can ignore gravitational potential energy within this question. Okay. We also know that the speed of the rock was initially 0. We are looking for the kinetic energy that it has when you launch it. Now, part B is going to change this, but for part A, I'm going to assume ideal conditions. And again, that will be the difference between part A and part B. So ideal conditions means that I am assuming that all of my energy is being preserved in the form of mechanical energy. So in other words, if I write it up more formally, it would look like this. The mechanical energy you end with is equal to mechanical energy you started with, allowing for the fact that maybe non-conservative forces did work along the way. Well, the only forces that would be present on a rock, the only relevant force at least, would be from this rubber band. And just like the force of gravity, the rubber band is a specialized force. It's a force that we'll ultimately introduce later as being a conservative force. So there was no non-conservative forces doing work in part A. So the kinetic energy that it ends with, plus the gravitational potential energy that it ends with, plus, I'm going to write it as the spring potential energy that it ends with, forgot the prime there, is equal to the kinetic energy plus the gravitational potential energy, plus the spring potential energy, like so. And it's true, as we introduce more forms of energy, as they become relevant to problems, we can just kind of build on this model, which is one of the reasons this becomes such a powerful approach. However, this simplifies tremendously because we already know that the gravitational potential energy I've set to be 0, it didn't change at any point. And even if I hadn't done that, just the fact that U gravity and U gravity prime are the same value, this rock didn't move vertically at all in the launch. Whatever the values were, if not 0, they would drop out of the equation anyway. I'm assuming that US prime is 0 because by the time this is launched, the rubber band would no longer be stretched out. We know that it started from rest, and so, surprise of surprises, we see something that hopefully was intuitive all along, but my equation somewhat formalized it. The equation basically that I come up with is the kinetic energy that you end up with is equal to the energy that was stored initially in that spring. So under ideal conditions, whatever the energy that was stored in the spring is ultimately given to the rock in the form of kinetic energy. Now, we weren't even asked for a speed or anything like that in this question, so all that I need to do here is say that we have that 100 joule value. And that really is all it was asked for in part A. How much kinetic energy will the rock have when it leaves? The answer is 100 joules. All of that energy stored in the slingshot, given ideal conditions, are given to the rock in the form of kinetic energy. So that's it for part A. Part B does modify that a little bit. It says explicitly we're no longer considering ideal conditions. How fast will the rock leave the slingshot if it loses 10 joules to some strange effects? I don't know, maybe there was imperfections in the rubber band, or maybe there was air resistance, or who knows what it was. There's just something wrong here. We lost 10 joules. So to account for that, what I'm going to do is I'm going to say there actually was a net work done by non-conservative forces. Specifically, it robbed us, it took away 10 joules. So I'm going to record this as negative 10 joules. Friendly reminder that work and energy is scalar. This is not a directional negative. It doesn't really mean to the left or down or anything like that. It literally means it removed 10 joules. And it's starting to be around now that you're going to see the utility of this mechanical energy conservation equation. We're going to be able to handle things that just go beyond kinematics. So here we go. Oh, and we want to know what was the speed of the rock after it was launched. Okay, so just like before, I'm going to say the mechanical energy that we end with is equal to the mechanical energy that it started with plus the net work done by non-conservative forces. And it's true, non-conservative forces can provide us with extra energy, or in this case, they can take away some of our energy, removing it to non-mechanical forms. In this case, heat and sound, I think, both of which are non-mechanical forms of energy. Okay, so K prime plus U gravity prime plus U spring prime. This is just like before, part A, except the details will change very soon, equal to the kinetic energy, the gravitational potential energy, the spring potential energy, and I didn't get to cross it out this time, the work done by non-conservative forces. Okay, but what is zero here? Well, the gravitational potential energy in both cases, there is no vertical motion once again, so zero. The spring is done by the time the rock launches. The rock started from rest, and that's it. That means that the kinetic energy, this is worth writing separately, the kinetic energy that we end with is equal to the spring potential energy that we started with, plus, this time it is not zero, there was an energy transfer. In this case, an energy transfer out of our system. We no longer have that mechanical energy. So, if you want to know the speed of the object, I can write 1/2 mv prime squared equal to, well, the spring potential energy, we knew how much it was, and the net work by non-conservative forces, we were basically told that much, or I realized it was negative 10. So if you want to know the speed, we can solve for speed v prime by, first of all, multiplying both sides of the equation by 2, so 2 times u spring plus the net work done by non-conservative forces, dividing both sides by m, and taking the square root of that. That would be a good way to solve for v prime. So v prime is equal to the square root of 2 times the energy stored in the spring, which was 100 joules, plus the negative 10 joules that was robbed from us, so ultimately we're down to 90 joules. But our equation will take care of that for us, all of which is over the mass of this rock, which we had up here. I recorded it as 0.705 kilograms, so 0.705 kilograms. So getting this into my calculator, root of the following, 2 times that divided by that, 0.705. So I get an answer of 15.978 to 3 figures. I'm just going to record that as 16.0 meters per second. And that will do for question number 5.